In this video, we're going to go over section 6.6 from our textbook, which is on log and exponential applications. So we'll start with this formula here, which is our formula for population growth or decay. This A of t here represents the total population after some time t. A naught is going to be our initial quantity. T represents time in years. And then this k here is going to be our growth constant or a decay constant, depending on the sign of k here. Right? And this is how each function behaves if we have a positive k or a negative k here. All right, so let's look at an example here. We're told that the amount of carbon-14 present in paint after 2 years is given by this guy here. We're also told that the paint contains 18% of its original carbon-14. With this information, we want to estimate the age of the paint. So, like I said, we're told that the paint contains 18% of its original amount of carbon-14. So after some time t that we're trying to find, this tells us that our population at this time t is equal to 18% of the original amount of our carbon-14. So this tells us that A of t is going to be equal to 0.18 times our A naught, our original amount. So plugging this into our formula above, we get this guy here. All right. We have A naught on both sides of our equation, so these guys cancel. We're left with 0.18 is equal to this guy here. And we can use our natural log to bring this exponent down. So taking the natural log on both sides, remember ln and e are inverses of each other. So we'll get ln of 0.18 on the left-hand side. And on the right-hand side, this exponent comes down. Right, now we just want to solve for t, so we'll divide by negative 0.00012 on both sides. So we get t is equal to this guy here. And then plugging this into our calculator, we get about this here. And then we want to round our answer to the nearest whole year. So this will be equal to this guy here. So about 14,290 years is how old the paint is. All right, let's look at another example here. Now we're looking at the half-life. So we're told that the half-life of a radioactive substance is 34.7 years. We want to find the exponential decay model for this substance, which is of this form here. And we'll round this answer to the nearest thousandth. Since we're talking about the half-life, this tells us that when t is equal to 34.7, so at 34.7 years, our population at that time is going to be half of our original population. So, plugging this into our formula of this form and plugging in our other given information, the fact that t is equal to 34.7, we get 1/2 A naught is equal to A naught times e to the negative k times t, which is 34.7. Again, these guys cancel, and so we're left with 1/2 is equal to e to the negative 34.7 times k. So what we want to do in this case is then solve for k, solve for our decay constant. What we'll do is take the natural log on both sides of our equation. So we get ln of 1/2 is equal to negative 34.7k. And then solving for k, we get roughly that there, and then we want to round to the nearest thousandth. So doing so, we get this here. So we just solved for k. We also know that t is equal to 34.7, so we can write the exponential decay model as follows. So this will be our exponential decay model dependent on our time t. All right, so the next example we'll look at also has to do with half-life. We're told that the half-life of a radioactive substance is 38.9 years. And first we want to find the exponential decay model for this substance, similar to that of the last example. So following the same reasoning as the last example here, we know that if the half-life of some substance is this here, then this tells us that when t is equal to that, our population at time t is going to be 1/2 of our initial amount here, our initial population. So using the same reasoning, we have that our A of t is going to be 1/2 times A naught when t is equal to 38.9. What we want to do is find our k here, and we know that we're going to have this minus here because we're looking at exponential decay. So these guys will cancel here. We'll get 1/2 is equal to e to the negative 38.9k. And again, using our natural log here, we'll get ln of 1/2 is going to be equal to negative 38.9k. And then solving for k by dividing by negative 38.9 on both sides. We'll get this here, which we are going to round to the nearest thousandth. So that'll be about this here. And so this tells us our exponential decay model is going to be given by this here, depending on our time t. All right, so we're going to use this to solve part B next. We want to figure out how long it'll take a sample of 500 grams to decay to 400 grams. So we want to find at what time t will our A of t be 400 grams if we started with a sample of 500 grams. So we'll plug this information into our model that we found in part A here. So we know A of t is going to be 400. Our A naught is going to be 500. And we want to find t. First, we'll divide by 500 on both sides. And then simplifying this guy, 400 divided by 500 simplifies to 4/5. And we get e to the negative 0.018 t on the right-hand side. Again, using our natural log here, we get this here, and then we can solve for t. And don't forget the minus sign here. So we'll divide by negative 0.018 to solve for t. So we get that t is going to be approximately equal to 12.4 years. And this is because we are rounding to our nearest hundredth. And then lastly, for part C, we want to figure out how much of the sample of 500 grams will remain after 20 years. So we're starting with 500 grams, so that'll be our A naught. We want to find the population A of t after 20 years. Evaluating this here, we will get this. And then we want to round to the nearest integer. So this is approximately equal to 349 grams will be left after 20 years. All right. Next, we want to look at this example here. We're going to use this formula here, where P is the present value of A dollars, T years from now, earning an annual interest R compounded in times per year. Okay, so that's what each of these variables represent. We want to find the present value of $200,000 10 years from now if interest is compounded annually at 12.2%. So we know that we're starting with $200,000, that'll be P. T is going to be 10, because we're looking at 10 years from now. We're compounding annually, so N is going to be 1, and our rate is going to be 12.2%, which we need to write as a decimal, so we'll get 0.122. So plugging this information into our formula above, actually, sorry, this should be A here. All right, so using the formula above, we get this here. Evaluating what's inside the parentheses, we get approximately $63,255 here. We're told that as age increases, so does the likelihood of a particular disease. The fraction of people X years old with the disease is modeled by this function here. We want to figure out at what age does this likelihood equal 50%. Okay, so this tells us that f of x is going to be equal to 50, and then we want to solve for x here to determine the age. So plugging this into our function here, we'll get this here. And then we want to solve for x. The first thing that I'll do is I'll multiply this whole thing on both sides. So this will be equal to 0.8. Then I'll divide by 0.5 on both sides. Doing so, we get this on the left-hand side, and then 0.8 divided by 0.5 is going to be 1.6 on the right-hand side. All right, next thing we'll do is subtract 1 on both sides. So we'll get 271 times e to the negative 0.122x. It's going to be equal to 0.6. Next up, we'll divide by 271 on both sides. We'll get e to the negative 0.122x will be equal to 0.6 divided by 271. And then again, we'll use our natural log here to bring this exponent down. So we'll get negative 0.122x equal to ln of 0.6 divided by 271. And then lastly, we'll divide by this guy on both sides to get x alone. Doing so, we'll plug this into our calculator, and we'll get 50.106, and then we're going to round this to our nearest integer. So this will be roughly 50 years is when the likelihood of a particular disease will equal 50%. All right, so that'll be it for this video.